All right, we are going to start on section 4.4, theorems about zeros and polynomial functions. Let's get started. We're going to be talking specifically about polynomials with their zeros when they're given to us. For polynomial functions with integer coefficients, we find the rational zeros and the other zeros if possible. Sometimes they're not possible. And we're going to use Descartes' rule of signs to find information about the numbers of real zeros in a polynomial function with real coefficients. All right. We're going to start with the fundamental theorem of algebra. And basically what that boils down to is that for every polynomial function that has a degree that is equal to or greater than 1, has at least one zero in the set of complex numbers. Now, that doesn't mean there has to be a real number, but there does have to be a complex number. All right, we're going to talk about how we can find out how many real numbers there are towards the end of this lesson. Okay, we're going to find a polynomial function of degree 3 having zeros of 1, 3i, and negative 3i. All right, and they're telling us what the zeros are. So, and I want to point out one thing here. And let me write it on my... here I have a 3i, whoops. Here I have a 3i, and here I have a negative 3i. Those two are together. You do not get to have one or the other. You have to have both, and we'll get into some of the reasons for that as well. All right, so we're given these numbers as a zero, so we're going to set it up. Here's my x minus 1. There's one of my zeros. I have my x minus 3i, which is 1 right there. And then I have my x minus a negative 3i, which becomes a plus i. All right, so we're going to go ahead. We have an a. In this case, we're going to assume that it's a 1. It can be any number that's not 0. All right. Okay, we can then multiply the factors. We're going to get this. If you take a look, this is one of those ones, and this is one of the reasons why it's really cool to use these numbers. This is one of the ones where if I take this x minus 3i and x plus 3i, I'm going to get the squares of each of those. So I'm going to have an x squared minus my 9i squared, which we've got a negative here. This becomes a negative 1. So this becomes x, what did they do here? Yep, so x plus 9. Okay, and then here we're going to just multiply through by the x, right? And then we multiply through by the 1. So through the whole thing, we wind up with x to the third minus x squared plus 9x minus 9. And we can go through, I'll show this on a worked out solution on a different video. Okay, so I want to point out that it is possible to have just complex solutions. In that case, you are going to have you're going to have non-real zeros, okay, which means we're going to have a complex information. Now, if we do that on our calculator, if we were to use something that, let me click it out of here. If I was to look for square root of 1, or square root of negative 1, we're going to be told on our calculators that it's a non-real answer. Now, we know that the square root of negative 1 is I. And as things stand on most people's calculators, this is going to just be in our real presentation. One thing you can do to help yourself out, and it's completely allowed, is to go into your mode, and we're going to come down here. Instead of having it be the real numbers, right? There's our real numbers. We're going to go over here and then hit enter. And now I'm looking at the complex numbers. I'm looking at the real and the imaginary part. Okay, there's three different ways that we normally write numbers. This last one is polar. We're not going to worry about that, but it is important to know. All right, so now we've got our complex numbers. I'm going to quit out of here now. And I'm going to do the same. And I have my I. All right, so it's possible to use your calculator as a solution or to find your solution even when you have irrational or complex values, okay? And that's going to come in handy. We're going to actually do some of that. All right. So if you have a complex number where b in the bi, the imaginary part, is not 0, it is you have to have its conjugate. There's no option in that. You must have its conjugate. So if you have a minus bi, then you have to have the a plus bi. All right, so in this example we have 2 plus 7i, which means that we have to have, there's no other option, we have to have a 2 minus 7i as a 0. Our non-real zeros also occur as, all non-real zeros occur in conjugate pairs. All right, that's also the same for irrational. Okay, irrational must also have a both the number and its conjugate must be in the event that the b, in this case, under the square root, is not a perfect square. If you have a perfect square, this does not apply. But if you don't have a perfect square, right? In this case, they give an example of -3 plus 5 square root 2. If that's a 0 of the function, then its conjugate is also a 0. So you'd have -3 minus the 5 square root 2, right? You can't have one or the other. You have to have both. All right, so we're going to go ahead and look at a polynomial function of degree 6 with rational coefficients. And they give us the rational coefficients. So we have 2 plus 5i, that's one number. We have a -2i, that's another number. And we have a 1 minus square root of 3. Those are 3 of the zeros. So the other 3 zeros are the conjugates. Remember, our conjugate says on this second term, right, the second half of this, so our imaginary part, we would have to change the sign. So in this case, we would have a -2 plus 5i has a conjugate of -2i minus 5, or -2 minus 5i. All right, for our -2i, we're going to have a 2i. And when we have a 1 minus the square root of 3, we're going to have a 1 plus the square root of 3. All right, so there's no other options. You cannot have more than that, since we have 6 as our degree, and we have to have both of those sets of numbers. You have to have the original number and its conjugate. All right, so rational zeros theorem, where all the coefficients are integers. You have this a sub n with an x raised to the n power, and so on. When they're relatively prime, you can have a p divided by q. Then p is a factor of a naught, which is the very tail end one, right? This very end one. And then the very first one is our a sub n. So that becomes our q. All right, so moving along here, we'll actually, I realize this is really abstract, really esoteric at this point. Let's take a look at some actual more practical examples. All right, in this case, we're going to take a look at this 3. This is our a sub n, because there is no exponent greater than that 4. And here is our a sub naught, or a naught. All right, and we're going to set those possibilities. This is going to give us like our possibilities here. All right, we find our factors for a sub n, right? Our factors for a sub n are going to be 1 and 3, right? This is a pretty straightforward. So that's our factors of 3. And then here's our factors of 4. We have a 1 and a 4, and then we have a 2 times 2. So factors of 4. All right, so in this case, I'm going to start with my denominator being the 1, right? And I'm going to have a 1 over 1 is 1. Negative 1 over 1 is a negative 1. 2 over 1 is a 2. Negative 2 over 1 is going to give you a negative 2, and so on. You're basically going to create all of the possibilities here. All right. We know that there's at most 3 distinct zeros because they have a degree. Well, it should be a 4, I think. There are the possibility of 4 factors. Yeah, because I think they made a mistake here, because this should be a 4, because this exponent is a 4. Yeah. All right, so we're going to use our synthetic division, and we're going to find our formula here. Remember, when we're doing this, this is really our x plus 1, right? What happens is we're going to set this x plus 1 equal to 0. That leaves us, when we move everything around, I'm going to have an x equals a negative 1, which is where this comes in. So this becomes our multiplier. All right, they made a couple of mistakes in writing this up. So here I have my 3 that I bring down. That's the first thing I bring down. Okay, so I have 3 times a negative 1. That's going to get me a negative 3. These two together give me a negative 14, right? So this is going to get multiplied by a negative 1, which means I have a positive 14. I have a 0 plus 14 is 14. Again, I'm going to take that, multiply by the negative 1. So this becomes a 10 minus 14. That's going to leave me with a negative 4. And then negative 4, when I multiply this by the negative 1, makes it positive 4. So this goes to 0. My remainder in this case is 0. So this is a solution. All right. So we can see that this is a factor. If this goes to 0, then it is a solution. All right. So in this case, we're going to go back and try a 2/3. I'm using the ones that I know work instead of having us go through all of them. So here, and actually I'm going to go back and show you where these numbers are coming from. This is one of our numbers, right? This is one of our numbers right here. And then our 2/3 is another of our numbers. All right, so moving back to we're going to do our synthetic division. 2/3 is our multiplier in this case. We're going to take our 3 to come down. 2/3 of 3 is going to be a 2. Negative 14 plus 2 gets me 12. Well, 2/3 of 12 is going to get me a negative 12, gets me a negative 8. So I have a 14 minus 8 is going to get me a 6. Now if I take my 6 and multiply it by 2/3, I get a 4. And that negative 4 and positive 4 goes to 0. So this is a solution. All right, this is a solution. Now, we've solved for 2 of our real rational numbers. If you take a look, that's what we said we were going to go after. We're looking for the rational zeros, right? That does not give us our irrational numbers, does not give us complex numbers at all. All right. So the thing to note here is that we now have a quadratic. All right, and this is really simple at this point to plug in and find our answer. So what we would have is, and you can do this other ways as well, but you can take your 3x squared minus 12 plus 6, or 12x I should say, 12x plus 6, and plug it into my quadratic equation. And when you get all done, and I'm not going to spend the time to do this right at the moment, I'll do this in the work. I'm going to show the work in another video. Then I'm going to go ahead and we're going to use our quadratic solution, that minus b plus and minus square root of b squared minus 4ac all over 2a. We're going to use that and find out that our solution is going to be the plus and minus of 2 plus and minus square root of 2. All right, remember I have to have both of those because I have an irrational number here. So I have to have both the positive and its conjugate, right, which is the negative side of that. Actually, I'm going to stop at this point. This is getting a little long, so I want to stop here and then we'll pick up on the next video.